Good afternoon, everyone. Welcome to the International Seminar Series at Javeriana University. This is the Master's Program in Civil Engineering. Today we have Dr. Sihyun Kim. He has got a Civil Engineering Bachelor's at Yonsei University in Seoul. And then he's got a master's and a PhD at the Georgia Institute of Technology, master's in 2002, and a doctor's degree in 2014. Right now, he's assistant professor in Bradley University, Illinois, the United States. And he's got a lot of professional registrations, participations, and honors. Uh, the most recent one in the Bradley University Parents Association as a Parents Association Award of Excellence. And in the past 3 years, he's got more than 9 publications in journals on his matter. Today, he's going to share with us his presentation named the Shear Band and Landslide Dynamics in Submerged and Subaerial Slopes. Dr. Kim, thank you very much for accepting our invitation to Javeriana University. The room is yours.
Okay, thank you very much to introduce me. And I feel really thankful to have an opportunity to share my research topic here. And I still remember that Joan, actually, he and I was graduate students together at Georgia Tech. And he was such an energetic person, and he was always motivating other students around him. And he never hesitated to ask questions, and so that's what little worries me today. And so again, yeah, my name is Sihyun Kim. I'm from South Korea, so I cannot really speak the Spanish at all. So anyway, so the presentation I'm going to do today is actually my PhD study is titled as, you can see that one, shear band and landslide dynamics and submerged and subaerial slopes. But this is mainly about the submarine landslide model, and we're going to talk about little by little. So again, as I said, this is my PhD study. So the co-authors of this presentation should be my PhD advisor, Dr. Jurmanovich, and my co-advisor, Dr. Puzrin in ETH Zurich. And this project was funded by US National Science Foundation. And I have some issues here, but anyway. So I'm going to actually start talking about the, obviously, motivation and background of this study. And as I said, I'm going to develop the landslide model, and I treated landslide I treated landslide as caused by dynamic propagation of the shear band and the underneath of the landslide. And I will show you how to use this model for the actual examples of the submarine landslide. And also, I will investigate to estimate the tsunami height, which is generated from the submarine landslide, and then I will conclude this talk. Okay, so submarine landslide is typically a pretty large landslide, and it is it's much larger than the on-land landslide. I don't want to give you the exact number, but typically you can consider that one submarine landslide could be as big as about 100 kilometers. But considering the most of the landslide, an on-land landslide, like a subaerial landslides, are probably about up to a few kilometers, you can consider that one is about 100 times 100 times actually different, 100 times larger than that one. And it is typically happening in a pretty mild slope. It's about 0.5 degrees to 6 degrees. And compared to the length, there's a relatively small thickness, which is up to probably 100 meters. And you may say 100 meters is still a pretty large number, but compared to the thickness, compared to the length, is fairly flat. And definitely, this is definitely largest landslide on Earth, so it plays a very important role of the mass transfer mechanism. And the submarine landslide is actually pretty common in the continental slopes. And what you can see in this image here is east coast of the United States, but you can, and this red portions, red areas are basically landslide scars are, the area of landslide scars are observed. But you can imagine that on the west coast of the United States and Gulf of Mexico, we have basically similar, the frequency of the submarine landslides were observed. And I believe in case of the Colombia, I mean, there must be also quite a bit of submarine landslides out there. And the trouble of the submarine landslides is definitely we have some submarine structures, for example, like petroleum platforms or the pipelines. So when you have a submarine landslide, that will affect these petroleum productions. Or I'm really sorry about the slides here, but sorry, maybe I should go back and forth a little bit. But maybe the little more general issues of the submarine landslide is it can generate the tsunamis, and that can cause a bunch of human casualties. So and you still remember that in the 2014 tsunami in Japan. Oh, I'm sorry, 2010 tsunami in Japan. Okay, so submarine landslide can be categorized into a few different types of the landslides. And in many cases, actually, the combination of these few categories. But in terms of the geometry of the landslide, we can say that landslides are going to be either rotational landslide or translational landslide. And the rotational landslides are basically slip surface, and slope surfaces are not parallel. So typically sliding surfaces are like a circular shape of it. The translational landslide is when the slip surface and sliding surface and the slope surface are nearly parallel. So many submarine landslides can be categorized as a translational type of the landslide. And in terms of the speed of the landslide, we can say that there are progressive landslide and catastrophic landslides. And when we say that progressive landslide, this is pretty slow landslide, typically maybe few centimeters per year. So we can say that this is a pretty stable landslide, and we can say that we can probably analyze that one in the static model. But there are catastrophic landslides, which is a pretty fast one, and we consider that one, it can be as fast as few tens of centimeters per second, so which is a pretty unstable landslide. And so in this case, we definitely need some dynamic analysis of the model. So these are some examples of the actual submarine landslide observed in the west coast of the United States and the offshore Santa Barbara, California. And what you see from the left side is a Goleta slide, and maybe you can say that this is kind of the rotational landslide. So you can see that the thickness of the slide is not really uniform. But if you see the left side of it, you can see the Gaviota slide. And in this Gaviota slide, you can see that the thickness of the the landslide is pretty uniform. So we can consider this is a translational landslide. But when I first look at this image, what captivated me is right next to the Gaviota slide, we have some fracture patterns, right the east side of the Gaviota slide. So so what puzzles me here is, so we do have a Gaviota slide, and we do have a fracture right next to it. And how come this fracture did not really grow to the global failure of the like Gaviota slide? And I'm going to explain this one with my model a little bit later, but I was not the first one actually to question that kind of feature. And so in the other references, I could see that people were interested in the same thing. So we have again the slides on the left side, and we have a fracture in the right side of it. And the way people analyze it here is in the Gaviota slide in the left side of the left image is basically we do have significant sliding of the mass movement. So it's not completely washed away, but still there. Part of them are still on the sliding surface, but the mass is slid down, and some of them still stay there. Some of them actually moved up to the original slope surface, whereas this headscar part, we may have some fracture there, but this fracture is not fully processed. So we may have some weak zone and underneath the sliding material, but we don't, I mean, this is not really completely created landslide. So basically, my story is like this. We may have some progressive movement of the landslide. Let me actually show you this image again. This animation again. Probably this seems like a serious issues on this presentation. But anyway, we do have some, sorry about that. We do have some progressive failure again. And then all of a sudden, probably catastrophic, catastrophic fast dynamic failure, dynamic propagation of this shear band created. And once we have a catastrophic the propagation of the the propagation of the shear band, it will create the active failure at the top and the passive failure at the bottom. And so it is making the global slope failure. And if this material has a global failure, this will jump onto the original slope surface, like with this gray arrow. Excuse me. And then it will create the wave generation and the water surface, and when the material is actually sliding down on the slope, and you can actually see that the tsunami can be generated in the two different ways. The one direction, which is moving rightwards, in this case, is moving with the landslide, so it is moving towards the ocean side. And there will be another tsunami wave will be generated basically the opposite side of the landslide direction, which is coming to the seashore areas, and that will probably create the tsunamis in seashore areas. But my interest here is, my first interest here is then what is the mechanism of the submarine landslide initiations, and then how the landslide is actually created before generating tsunami. So again, go back a little bit back here. So perhaps the geometry of the submarine landslide is pretty flat and pretty lengthy condition, probably because of such a things. And many researchers has been trying to use the infinite slope model to understand the submarine landslide. And this is a very, very traditional model, as probably all of you already have a great idea about what it is. It's nothing but actually the force equilibrium condition, and we can calculate the factor of safety for this condition, which is when you have a shear resistance is smaller than the gravitational shear stress tau g, then probably the factor of safety is going to be 1, and the failure will happen. The good thing about this one here is we can still see that one if the in the submarine condition, if you have some the extra large pore water pressure, then the shear resistance will be reduced. So then factor of safety will be reduced, and so we will have the landslide is happening. So basically, we can show here how the landslide is happening. But there are a few questions I had about this model, which is, the first thing here is, since this element, this shaded element, is basically representing the entire slope surfaces. So if you try to use this infinite slope model, and for your research, probably you realize that we cannot really estimate the failure size, because it is infinite slope model. We don't have any initial point. We don't have any ending point. So we don't have a beginning of the slide or the end of the slide. So basically, the failure this is happening not only this element, but the entire element. So which means this model cannot naturally explain what is a failure size or failure length or failure volume. Another thing here is, since this failure is happening all of a sudden, and but in fact, in the reality, probably some part of the slope failed first, and then that will actually propagate all of a sudden. I mean, it will propagate the entire slide surface. But since in this equilibrium, the limiting equilibrium infinite slope is considering the failure is happening all of a sudden, doesn't have any movement before the global failure. So which means when we have the global failure, or onset of the landslide, we don't have any we don't have any initial velocity. We call it, this is a initial velocity. And obviously, if you try to think about the tsunami magnitude, this failure volume, or the size of the landslide, and the velocity of the landslide, are definitely key factors and key parameters to estimate the tsunami magnitude. So I wanted to answer these questions for this study. So the idea of basically small initial wick zone and its propagation of the wick zone, or its propagation of the shear bend in slope, was first suggested by the guy, his name is Palmer and Rice, in 1973. This was probably the first model. I've looked at it, and in this model, what they did here is they used a fracture mechanics theory, and they calculated a fracture energy at the tip from this plot here. And then they set the fracture propagation condition when the energy surplus of this slope is bigger than this fracture energy, then the fracture will be propagated, or shear bend will be propagated. If it is not, if the energy surplus is smaller than this fracture energy, then the shear bend is not going to be propagated, and it's going to be stay stably. So from this fracture propagation condition, we can calculate the critical length, which is, if the shear bend length is smaller than critical length, then it is going to be safe, even though we have a certain shear bendability. But if the shear bend length is larger than critical length, then this will go for the catastrophic failure. So the slope is not going to be safe anymore. The bad thing about this model, I'm sorry to say about the bad thing, the problem of this model here is, let me try to use my mouse here, and this region, which is basically the dark gray box at the top of the landslide, at the top of this shear bend, needs to have pretty large tensile strength over there, because the entire material is basically hanging at the top of this shear bend. So and so that means, if you want to have this upslope propagation of the shear bend, we should have certain tensile strength, and which is not pretty common in the submarine landslide condition, especially saturated condition. And in fact, this Palmer and Rice model was developed for the over-consolidated clay, which has some non-zero tensile strength. But this is not really applicable for the submarine landslide condition. So that's why, back in 2004, me and my advisors we're changing the model a little bit, and we flip the propagation direction in the downward direction. So in this case, this one is definitely pretty close to the gaviota slide we observed it over there. And in this case, we have active pressure at the top of the slide, and the after and the lower than this top slide, and the lower part has always compressed by self-weight. So entire slide is in the compressive condition. So we never need to worry about the tensile strength of the material. And we can consider again the energy balance. So we can calculate the surplus energy surplus, and we can compare with the surface the fracture surface energy. So we can calculate the critical length in the same concept. Again, if the shear bend is larger than critical length, we are going to have a pretty unstable slide. And not only this one, we can actually continue to think about, so what's happening then after the critical length. So after the critical length, the shear bend will be further propagated and until it reaches the failure length. And this failure length is going to be defined as when the supporting stresses on the bottom of the slide, bottom of the shear bend is equal to the passive stress. So basically, when you have a passive failure, that is going to be the condition for the global failure. So in this condition, so in this passive failure condition, we can say that, hey, a static analysis of the landslide is achieved here. But the trouble of this one, the achievement of this model here, is that we can explain what is happening after the critical length. So basically, after with the catastrophic failure. But the trouble of this problem was still the entire material is happening simultaneously. So the material here between the PA and PP in or the size of the LF, the failure length is basically accelerated from the initial slide velocity. So this brings the motivation of my dynamic model. So in the dynamic model, we can actually consider that one the wave generated from the fracture tip. And we do know that at the fracture tip, when the material is breaking, the fracture is actually emanating from the tip. And in this condition, the wave can be propagated. Wave is actually generated in all possible directions. But in the downward direction, the wave is not going to be reflected back to the fracture tip. And also, if you try to think about the vertically down, it's not a vertically down, but the perpendicularly downward direction, the wave is also does not play any role. But if you try to think about the wave is moving to the upward direction, and this one is actually touching back from the top end of the slide and coming back from the wave. So we should probably think about this reflection wave as well. And also, even before we talk about the reflection wave, this stress wave is actually propagating upward direction, which means this wave is basically decreasing the gravitational shear stresses. So basically, this wave is unloads the loads, the self weight of the slide. So possibly passive failure at the bottom tip is going to be somewhat delayed compared to the static analysis, and which will result in possibly again the greater shear bend length before the slide, the global slide is happening. So that means the global failure, the landslide volume is going to be also could be getting bigger. And another thing here is, since we have some wave movements along the band, so we can probably think about the slide will have some non-zero initial velocity when we have the global failure. So the motivation of this study is, to summarize it, we wanted to calculate what is that then initial landslide velocity. And again, this is basically at the onset condition of the slide separation. And also another thing here is what will be the landslide size, or what is going to be the realistic failure length of it. And then what will be the impact on the tsunami magnitude? So I first set the my dynamic model here with the again the downward propagation direction. But the initial condition of the dynamic model is actually starting from the end of the static model, which is a critical length here. Because the shear band is propagated from the critical length. So at the so initial condition is basically when the length is same as critical length, and then we can think about the equation of motions, and it turns out it is pretty close to the wave equation, but it's like a forced wave equations. And uh, initial condition of this model has the displacement, the relative displacement has a static relative displacement, and that is the initial condition. And the velocity of this model is going to be 0 initially. And then, in terms of the boundary condition, in the left end, which is basically x is the horizontal, the coordinate is 0, we have an active stress, so we should think about the active strain. And at the fracture tip, when the horizontal the coordinate is the length of the fracture length, then and the relative slip is going to be 0, so displacement is going to be 0. And the propagation condition should be also changed. And the static condition, we can say that the strain gamma here is going to be same as gamma naught, which is a static fracture strain. But in the dynamic condition, it has to be changed. It is a function of the velocity, and it is also a function of n. And I'm going to talk about this n later. But keep in mind, in the dynamic condition, we have a different propagation condition compared to the static condition. And after that, I would like to actually introduce to you some new normalized parameters, which is a material velocity and this material strain here. And I know that this eta and gamma is not typically used the parameter in the civil engineering or geotechnical engineering, but in dynamic fracture mechanics, people typically use eta and gamma for the material velocity and strain. And using them, I also kind of constructed a few controlling parameters here. The first one is a strain ratio, which is a ratio between the critical static strain gamma naught and the gamma A, which is active strain. Again, I'm using gammas instead of epsilons, which is typically used. And the one thing here is a bluntness parameter, which is called the bluntness parameter, and it's basically n. And this little n here is a ratio of the fracture energy of static to dynamic fracture energy, or fracture strain ratio of the static to dynamic condition. And we do know that in the frictional theory and dynamic condition, the fracture energy is going to be smaller than the static condition, because material is easier to be separated in the dynamic condition. So typically this value n is larger than 1, but in many geotechnical materials, such as rock or soil or even concrete materials, the parameter value of the bluntness parameter, the exact value of the bluntness parameter is not known. Let me actually talk to you a little bit later, but this effect of the bluntness parameter is pretty minimal. So the way, this is the way I developed the exact solution here. So once we have the wave, the fracture is propagated from the L0 here, and then we will create certain wave, which is moving basically the left side of the slide here. And that will travel from point A to point C here in the X and T space, basically, or the space and time, the coordinates here. And then this, the reflected wave at the left end will be reflected back to the tip of the band. And by the time this wave is reflected to the band length, band A, this shear band tip is also propagating. It's also kind of moving out. So this reflected wave may or may not be able to actually meet the fracture tip. But probably, obviously, the simplest condition is going to be when the wave never meets the fracture tip. And we will work under this simplest case, but we can also work with the cases when the wave is meeting the fracture tip and reflected back to the left end. Anyway, along this characteristic line, if we are integrating the arbitrary point between A and C, which is a point B, and to the corresponding point P, then we can actually calculate what is the velocity at the fracture tip, which is basically a little complicated here, but the function of static strain and the fracture strain gamma naught n value of n here. And same way, we can actually calculate the material velocity and material strain at the tip of the shear band, and also any arbitrary point and x and t here. So so obviously you can see that one. This is a function of probably the value of gamma star. I'm sorry, lambda star and n. So in fact, it is the case. So if you take a look at here, when n value is 1.4 in the blue line here, the reflected wave will not actually come to the tip of the shear band here. But if the n is as small as 1.1 here, which is the orange line here, then the wave is reflected back to the fracture tip, and it is going to be reflected back to the end and coming back here again. So there will be some basically the travel in between the fracture tip and the left end of the slide. So we can see that one. This is definitely a function of n. So I wanted to think about a little bit simpler solution inside of this exact solution, which is the motivation of define this asymptotic solution here. And this asymptotic solution, I was assuming the shear band velocity is accelerated to wave of the elastic, the velocity of the elastic wave, which is a c here. So basically, this is outside the upper bound of the shear band velocity. So in this case, since the shear band propagation velocity and the wave velocity is the same, this wave never comes to the fracture tip. So this will be, I guess, the simplest condition. And this can be achieved by when the dynamic fracture strain is equals to 0. So which means it is really, really easy to create the dynamic fracture propagation, or the ratio between the static and dynamic is going to be infinity, because the static dynamic strain is the critical strain is a 0. So it sounds like it's a pretty huge assumption, but you will see that this is not actually the big assumption. So if you take a look at here, the distribution of the velocity and strain and the arbitrary time here, and if you take a look at the velocity here, the solid lines are asymptotic solution here, and the dashed lines are exact solutions here. So you can see that one, this exact solution and asymptotic solutions are not that different here. And if you take a look at the strain part, this is nearly identical, so you cannot really see that the difference between them one. So the reason, this was a little bit interesting to me. So I basically explored by changing back factor of changing the value of n here, changing from 1.001, which is a practically 1, to increasing 1.01, 1.1, and 2, and asymptotic solution, which is basically n is going to infinity. I use the typical slide properties here up here, and I checked failure length, I checked the slide velocity, and I checked the ratio between the dynamic failure length and the static failure length, and I checked the crack velocity or the shear band velocity here, V over C here. So you can see that the numbers are not really changing much, and except this initial velocity V naught. So that is because the shear band is accelerating pretty quickly. So when the shear band length is about 3 times of the initial length or the critical length, then the V over C, or the normalized shear band velocity, is already pretty close to 0.88, 0.9, or pretty equal to 1. So which means the shear band is accelerated pretty quickly, and it's pretty close to the elastic wave velocity even with a very short distance. So we can say that this asymptotic solution is basically the upper bound solution, but it's a fairly nice working upper bound solution here. So from this one, since we do have an exact solution, we can think about the slope failure condition. And again, when the strain at the tip is going to be equal to the passive strain, or when you have a passive failure condition. And I could calculate what is the failure length in this case. So this is a normalized the condition. Dynamic failure length is normalized by the initial length or the critical length. And it is a function of the lambda star and gamma naught and gamma p, which is a passive strain. And I've tested it for the to calculate I compare with this dynamics. The failure length is a static failure length, and the shapes are pretty similar. The formats are pretty similar, but actually I realized that the ratio between the dynamic failure length and the static failure length is a nearly factor of 2. So this is the actual case of the Currituck slides in the North Carolina, and we're going to talk about this one a little bit later. But there are 2 cases in the Currituck landslides. So the ratio between the dynamic failure length and the static failure length is about 1.9. So dynamic analysis, we can say that estimates roughly twice of the larger than the static analysis. And the reason of this one is, again, remember that the wave generated from the fracture tip is basically making some unload of the sliding surface. And since we do have the exact solution, we can also calculate what is the material velocity in the everywhere in this space, and especially certain specific time, or if we know the failure time, we can calculate the distribution of the material velocity, and that will give us some sliding velocity. And again, if you can calculate the failure length, then you can calculate the slide velocity at the moment of the failure, and that will give us that will give us the initial velocity with the separation of the material. And using this material, using the material slide velocity, we can actually calculate the effect of the water resistance, because the water resistance is typically the proportional to the second order of the slide velocity. And it turns out the water resistance was not really making a big impact unless the slide length is less than about 100 times of the initial critical length. So water resistance, it is actually start playing an important role for really large slide, extremely large slides. Again, the slide is about 100 times bigger than the critical length. So there will be some examples of the actual slide. Again, going back to the Gaviota slide that I introduced in the earlier, we have a headscarp here, and we do have the Gaviota slide on the left and the headscarp on the right. And this slide was actually happened about 200 years ago, and a fairly small landslide, about 0.2 cubic kilometers. The slope angle was about 4 degrees, and the slope thickness was about 12 meters. And failure length is recorded as 1 kilometer roughly. So if I use the dynamic model, and I realize that the initial length or critical length about 300 meters will be able to create the failure length of the 1 kilometer. In this case, I can calculate the slide velocity and the static and the failure and the initial length for when we do the static analysis. And if you take a look at the adjacent fracture right next to the Gaviota slide, if you try to get a little bit milder slope here, like for example, like a 3.8 degrees of the slope, with the same thickness condition, I could come up with the initial length is about 600 meters. So if the initial wick zone is anywhere between like a 300 meter and 600 meter, we can say that Gaviota slide, we can make a Gaviota slide failed and up to 1 kilometer of the length, and well as this adjacent fracture is going to be stable like that. And there's another example here, that probably I mentioned earlier, is a Kurituk slide, and which happened again about 20,000 years or 50,000 years ago in the offshore North Carolina. This one actually consists of the two separate slides, and people call it like a slide 1 and slide 2. And it's much bigger than the Gaviota slide, about 128 cubic kilometers. So so if you try to consider the slide 1 and slide 2, and which is what many people believed, if that is the case, basically slide 1 happens first, which is the downside of this model here. So if you are losing the bottom support here, so what people believe is a slide 2 happened because of loss of this failure, loss of the support. And the people believe it, the failure length is about 11 kilometers in the slide 2. But the question about in this analysis here is, we may actually consider this slide happens like a retrogressively, and the retrogressive slide means the slide failure, the slide 2 is happening little by little. But this is probably not the case, because from this submarine reports, submarine reconnaissance reports about the Kurituk slide, and they have a fairly smooth surface, very clean cut in the slide 2 area. And if you take a look at the examples of the retrogressive slide and this color picture, we have a bunch of residues in the sliding surface. So probably slide 2 is not happened and retrogressively. Or maybe another idea would be like using palm and rice condition. The shear bend was propagated in upward direction. But again, you probably remember that in this case, we need to think about the tensile strength. And if you want to have 11 kilometers of the failure length, based on my calculation, we need to have about 1 megapascal of the tensile strength, which is nearly impossible here. So this is the scenario I would like to suggest here. So we first had a upper slide actually happen first. And because of the upper slide, we are losing some effective stress in the second slide. So, and the lower slide. So lower slide actually happened right after the upper slide. That is my scenario. And so the slide length about 29 kilometers of this upper slide and 18 kilometers of the lower slide can happen with about 3.57 kilometers or 1.57 kilometers of the initial length. So if we have the initial wick zone about 3.5 and 1.5 kilometers, we can create the upper slide and the lower slide, and they will create the initial slide velocity about 1.5 and 1.9 meter per second. And there's another example here, is a pretty notorious Storegga slide, and this is one of the most famous underwater slide. It's in the offshore Norway, which has happened fairly long time ago. And actually, people believe that the Storegga landslide happened not at once. It is like happening in many different events. But assuming this entire Storegga slide is happened at the same time, we can actually model this one as well. Like 112 kilometers of the failure length can be achieved with only initial length of the 8.5 kilometers. So only 8.5 kilometers of the initial wick zone create the failure length of the 112 kilometers, and slide velocity is about a little less than 2 meters per second. And this St. Alban slide is a sub-aerial slide people also studied. And the people truly believe this one is like an uphill propagation condition. But if you model this one with the failure length is about 2 kilometers and the initial length is only 220 meters, is going to be enough to create the failure length about 2 kilometers. So before we are moving further, I would like to show a video to explain my topic, and I hope you enjoyed it. So let me play this movie again. So you can see that this experiment is pretty quite a large-scale experiment, and this is in fact done by my colleague and Dr. Fritz in Georgia Tech, and his colleagues in the Oregon State University. And in fact, this is not really a submarine landslide, it's a subaerial slide, but still, the reason I show you this video clip is when the soil moves inside of the water, it basically pushes water and it is generating basically ocean waves. So we've been talking about the submarine landslide, the submarine movement of the soil. So I want to actually, but I wanted to estimate so then how much tsunami is going to be generated with that kind of movements. So I basically work on the landslide motion, and then this landslide motion, I made some assumptions here that my slope angle is fairly mild, and my sliding, I mean, I can still including the friction between the baser surface, which is a sliding surface, and also the resistance against the water. And using the momentum balance equation here, I can actually calculate the slide velocity and the sliding distance. So you can see that one here, and in the between the dynamic condition and the static condition, basically they have a different patterns of the slide velocity and the sliding distance here. But what you can see in both conditions here is this both model actually shows where and when this slide stops here, and that is basically giving us how much the sliding distance we have it, and this is typically the common parameter to describe the landslide, and this is called the runout distance here. So so basically you can see that one between okay. And between in the slide velocity plot, you can see that one, this red line and the blue dashed line, which is dynamic and static condition, maximum slide velocity is not that different in this case. So after that, I was trying to calculate it, then how much wave is generated from this sliding movement. In this case, I try to do that some approximation here. I made some assumptions here, so to make our calculation is simpler. So I assumed here the shallow water approximation. In this case, I'm assuming the water depth is much smaller than the slide length, and the water depth is also greater than the surface wave amplitude and the slide thickness here. And using some normalized parameters, I could actually simplify this mass balance equation and the momentum balance equation of the water, and using the initial conditions here, and then and eta here is psi of here is basically normalized wave amplitude, or maybe the tsunami amplitude, and u is basically normalized the water speed here, and that they are zeros in the beginning. And the equation for the tsunami wave amplitude can be obtained from this momentum balance equation. And then this is the result for the upper Kurituk slide. And this is when the first image here shown here is when the slide is still in motion, which means slide is didn't actually reach the stopping distance or the run out distance. It's still sliding down. So the different the waveforms here, like blue, red, and greens, are basically the waveforms at different times. And obviously the red is the earliest one, and the blue is the second earliest, and the green is the last one. So before the slide is actually stopping inside of the water, the wave is pretty unstable, and they are not really, we don't see any patterns here. But if the slide stops there, even the slide stops there, basically the water wave is not stopping there. So you can see the backgoing wave and outgoing wave, which means actually the backgoing wave is the tsunami wave is opposite to the landslide direction, and outgoing wave is the tsunami wave is basically same direction of the slide direction, landslide direction. You can see the same wave patterns are basically propagated the backwards and outwards, right? So in the very vast wide ocean, we may need to think about the attenuation of this wave as well. But for now, I'm basically trying to calculate how much wave is basically generated here. So this is the upper slice of the critic slide, and you can see that when, again, the red is dynamic analysis and the blue is a static analysis. That one, you can actually see that the dynamic solution, which has basically double the magnitude of nearly double magnitude of the slide size and some initial wave velocity, you can say that when in the dynamic analysis tends to have much bigger the tsunami wave heights compared to the static analysis. And a little more interesting thing was actually lower critic slide. In the lower critic slide condition, the the analysis could estimate some wave speeds here, but some wave heights here about I think it was about 3.5 meter or something like that. But in the static condition, the wave was not really generated at all. And in the static analysis, the lower critic slide did not actually move from the original position. So we can say that when the tsunami magnitude is typically greater than in dynamic analysis. So to conclude this talk, I could find the basically exact solution, and which is dynamic solution for the shear band propagation, and which typically analyze in the infinite slope condition. And this dynamic analysis can assess both the shear band, the propagation velocity, and also initial landslide velocity and the landslide velocities as well. And this dynamic analysis is applicable for both uphill and downward shear band propagation condition, although we typically prefers to do it in a downhill condition or downward condition. And even with this, the exact solution, I developed a simpler asymptotic solution. But as I've shown you guys, that this asymptotic solution is not that much different from the exact solution. And the result is not really sensitive, because the reason here is that because of the factor of the n. And so even though we don't know about the magnitude of the n, but you can see that when the basically impact of the n is not that significant. And we checked the water resistance of the submarine landslide, and that was basically insignificant. And we also checked it in the dynamic analysis. Failure length can be estimated about twice larger than the static condition. And the effect of the initial velocity of the tsunami height was basically not really significant compared to the size of the landslides. Okay, that will conclude my talk. And thank you very much. And I'm very sorry for the the slide movement. And when I hit the button, and it kind of seems like it is automatically hitting like 4 or 5 times in the head. And hopefully that was not really bothering you too much. Thank you.
Thank you very much, Professor Kim. I'm going to open time for questions. Does anyone have questions about the presentation of Dr. Kim? There's one question, Dr. Kim.
Please go ahead.
Sihyun, it's Juan. Thank you so much
Yeah.
for the presentation.
Thank you.
I want to understand a little bit more about the nature of the wave that you mentioned that propagates back and bounces back, and it's part of the basis of your analysis. So is that the nature of that wave is literally a mechanical wave, like something that could be actually measured in the field?
Yes, it is a mechanical wave. Let me actually show that picture here.
Which I guess is in the nature of a P wave velocity type of thing.
It is hard to say it's a P wave, But remember that this one is basically two-dimensional analysis, right? It's basically plane strain analysis, and so this wave is basically I probably have it here. Here, this is elastic. This is elastic wave velocity, and then I put it here, Young's modulus E here, but this is actually plane strain modulus. Should be plane strain modulus, and the plane strain Young's modulus E. So and in the practical condition, yes, I mean if you have the dynamic landslide, yeah, obviously it is creating sound, heat, and stress wave as well. So we should be able to measure that wave speed. And if you can measure that wave speed, that will be actually more accurate analysis. Yes.
Yeah, well, yeah, my question is because, or my follow-up question will be, if I were to apply this technique to a subaerial then the mechanical wave will be sensitive to the water or the saturation content, right? Because if I were to talk about a P wave, that would be dependent upon the amount of water, but not a shear wave.
Yeah, that's absolutely right. I'm completely agree with you. And in fact, actually, my current research at the top of this topic here is try to mingle with this model with the unsaturated parameters, because as you know that in the unsaturated condition, material needs to be examined a completely different way. In a saturated condition, we can say that when, and in the submerged condition, the degree of saturation is basically homogeneous, at least. But in the on-land landslide, subaerial landslide, the degree of saturation is completely a function of the depth. So we need to consider then what would be the modulus, and we need to consider what would be the density. We need to consider what would be the active stress and passive stresses. So those are, yeah, and definitely that needs, there are many things need to be checked for that one.
Thanks.
All right, does anyone online have questions for Dr. Kim? You might raise your virtual hand. All right, Dr. Kim, there's a question on the chat.
Okay.
Do you have the option to read it? If not, I can read it. It says, does the moving mass considers any infiltration pressure or drag that damps the landslide runout?
I cannot understand the question. Can you say it again?
Okay, one more time. Does the moving mass considers any infiltration pressure or drag that damps the landslide runout?
Oh, not in my model. Yeah, and then obviously, yeah, we can consider that one for the. So let me move that parts here. So you're basically asking questions from here, right? So and in reality, probably yes. But as you can see that one, yeah, I want to basically make it clear the scope of this work, and I clearly understand that one, the landslide, and it's especially submarine landslide, is probably many submarine landslides are not really happening in the solid mechanics failure type, but basically the way I run and the way I create the model and the way I analyze this model is assuming that we are dealing with these basically solid mechanics, solid block movements, or solid mechanics here. And I know that there will be some people disagree with me, but what I want to say here is at least my model has some improvements from the conventional infinite slope model. So the same thing is here in the landslide motions, And in fact, yeah, there will be infiltration effect. There will be many other impacts, and this block is going to be probably, smooshed away inside of the water. So so stopping distance is going to be different. The run out distance is going to be different, and tsunami wave is going to be also different. Yes, I know that one, but that's, I would say that is not really my area. My major interest was like a landslide model. And I wanted to estimate it, then how much tsunami can be generated from my model, from my estimated model. So um, I hope I'm answering your question.
All right. I guess that's it. Dr. Kim, thank you very
Mhm.
much for being our guest today on the international seminar series at Javeriana. Thanks for your time, and we hope to count with your presence in future seminars as well.
Oh, thank you very much. And yeah, again, it was very good opportunity for me, and I was really happy to had a chance to talk to uh, uh, to in the school for my research topics. Okay, thank you.
Thank you so much.
Thank you.